And our last but not least speaker for today is Wang from the math department.
Hello, everyone. My name is Wang. I'm from Math Department. Today, I'm going to introduce a new approach to do uncertainty propagation. So we know that uncertainties are everywhere. So the main questions we want to address here are two aspects. One is in the forward setting, where you have uncertainties in the initial data, and you want to characterize how does this uncertainty carry over to the later solution. And also in the inverse setting is that, say, if you have uncertainties in your measurement, how does that affect your reconstruction parameters? So in the inverse setting, so let me introduce the inverse setting first. So let me write down this general framework where this U is the parameter and the Y is the state of interest or the measurable state. The major setup we have, the major question is, instead of the deterministic one where you think that you want to find the optimal parameter U such that it will lead you to the measurement as close to your data as possible, here we ask a different question. We say that, say, if this parameter U is stochastic a priori, so we want to recover a random parameter, then the question becomes, how do you recover a distribution of this parameter? So the key component in this question is we want to lift everything to the probability space. So instead of finding a vector, for example, a vector in your parameter space, we want to find a distribution over the probability space of your parameter space. So parallel to the deterministic problem that you are probably familiar with, we can also write down the corresponding variational problem. But now everything is in the probability space. So here, hopefully this cartoon will give you an idea. So the lower part is the deterministic inverse problem, where now we lift everything to the probability space. So then we want to recover the distribution. So parallel to the deterministic one, we can also address the following questions like how do you characterize the minimizer, how do you design the regularizer, and what's the stability of your variational problem, and then the most practical question is how do you find the minimizer. So the key feature of this new framework is that it has this built-in uncertainty and also has this connection to generative AI. So many generative AI methods can be used to find the minimizer here. So for those of you who are familiar with Bayesian inverse problem, you may wonder that this approach seems to be very similar to Bayesian. But actually, there is a key difference. So the key difference is that the Bayesian is actually a stochastic approach for deterministic inverse problem, where the new framework I'm proposing here is a deterministic approach to stochastic inverse problem. But we can easily make it a stochastic approach by including the noise. Okay, so then for the other aspect is the forward setting. So again, I'm writing this general abstract form. And now I want to, again, so you have this omega is a random variable. And now the question is, how do you characterize this randomness for a later solution? And there are two existent approach. Either you just draw samples, which is Monte Carlo, or you build a surrogate model like the generalized polynomial chaos. So each of them has its pros and cons. But here we propose a completely different approach. Again, we want to lift everything to the probability space. So instead of drawing samples or build surrogate models, we ask the question of, can we evolve the distribution of the solution directly? And so that's a more precise question. So can we find the evolution of this distribution solely based on the initial data? And if the answer is yes, then we completely overcome this curse of dimensionality. And also we can get a priori regularity estimate. So our recent work provides a concrete example of when this answer is yes. Okay, so that's all I want to say. So if you think this new framework is useful, feel free to talk to me.